coherent spin wave transport in an antiferromagnet. And in the course of this talk, I will try to show you how ultrashort pulses of light, especially tailored, can be interconverted into coherent into wave packet of coherent magnons, which actually can be used to transfer information. So I put it the title of my talk like word transport. So I would like to start a little bit with this transport phenomena, which we are all familiar with. So basically this electric transport. And we know that the electric transport is carried by an agent, which is known like electron. And the electron has a dual nature, as we all know. So it's basically both at the same time wave and a particle. But it's some kind of like this mystery of dual nature is kind of like if you talk about transport, we typically talk of electron as about particle only. And what's the reason for this? And actually, the reason behind this is quite simple, because even under action of external electric field, electron propagates as ballistically only a very short moment of time. Basically, like it experiences very quickly and very rapidly scattering. And this scattering event happens almost every 10 to 20 femtoseconds. So, and it behaves as a wave only within this very, very short amount of time, which is like 10 to 20 femtoseconds, and which correspond to a propagation path of 10 nanometers. So basically only on a length scale of 10 nanometers, you actually can make something, can make this electron something what can be related as to a wave. So basically to see interference of electrons. And what we see typically is scattering, and that's behavior typical for a particle. So, and it actually has a dramatic actually consequences for the electronic transport, and the main consequence of this one is actually enhanced dissipation and heating due to scattering. But actually, we are quite lucky that electron is not only one quasi-particle which can be used to transport information. There exists actually the whole quasi-particle zoo. Among them are many quasi-particles, very exotic, such as anyons or some topological defects, some amplitude modes, more trivial, such as phonons. We heard about phonons a lot today. But of course, like we're here for magnetic conference, so basically magnons is the most interesting object for us. Basically, let's have a look. So what magnons are? Magnons is it's a propagating or spin base. It's a propagating excitations in an array of magnetically ordered spins, which are exchange ordered. And magnons naturally have some advantages when compared to electrons. And first of all of them, it's basically very long coherent times, which are basically nearly 10 to 9 times longer than what we see by electronic transport. So it's way more easier to deal with them as with waves rather than with particles. Also, they have, as a consequence, and can maintain very long coherent times, spatial coherence of more than 1 millimeter. And that's basically this 1 millimeter is seen in this best ferromagnet ever, yttrium iron garnet, which Andrei mentioned today. And another advantage of spin waves for computing is actually the fact that they are highly nonlinear. So you can realize some computational operations. And indeed, a discipline which operates with spin waves is very much mature for the moment. It's known as magnonics, and it has a very, very much of developments. In particular, the logical gates have been realized, some devices for data buffering, and even all magnon transistors have been realized recently in a group of Andrei Chumak. But the problem that magnonics, its current implementations are all based on ferromagnets, and we would like to switch to antiferromagnets. And there's basically many reasons for this, why to switch to antiferromagnets. Actually, almost all material on Earth, actually, if they're insulators, most of them are antiferromagnets. And there's a quite simple quantum mechanical reason for this, but I'm not going to go into details. But we just take away a message that's basically a lot of antiferromagnets. And they, of course, host antiferromagnetic spin waves, which can be used to transport information. All right, they have also some advantages, as we know that actually they feature higher operational frequencies, which are typically in the terahertz range. But what is also even more important for the transport phenomena, they have higher spin wave group velocities. And these speeds typically can reach up to 20 kilometers per second. And while in ferromagnets, we typically deal with no more than 1 kilometer per second. Another advantage of antiferromagnets actually is the fact that their magnons they feature a linear dispersion for large k vectors. Actually, the linear dispersion is something what light has. So basically, it means that you are able to play this antiferromagnetic magnon in the very same way as you do with light. And the most appealing, maybe a most attractive thing what you can do with such magnons, actually, you can create also short pulses of antiferromagnetic magnons. And you can try to compress them, you can try to play with them. And that's due to the fact that it's linear. If it would be in ferromagnets, such a pulse, once created, would smear out immediately. However, if you would like to drive antiferromagnetic magnons, we can actually face some difficulties because their frequency in the terahertz range, and traditional sources to drive magnets, such as a microstrip antenna, they typically operate in they are basically electronic devices, and they operate in the frequency range below 0.1 terahertz. So basically, there's a problem that there's almost no sources to drive coherent antiferromagnetic magnons, but antiferromagnetic transport is very much appealing. That's why what people do, they at least try to realize incoherent DC spin transport in antiferromagnets. An idea here is pretty simple. So what you do, you make a local population of non-equilibrium antiferromagnetic magnons, and then they diffuse away. And then you're able to measure via some inverse spin effect, basically such a so-called diffusive magnon transport. And it's remarkable, actually, because this diffusive spin transport works very, very well in magnetic insulators, where there's basically no electrons, and you can transport information on distances more than 10 microns. So basically fantastic. But the problem is that this transport is diffusive. So basically it means that you don't know about frequency of these magnons, you don't know about the k vectors, you also don't know whether they really offer you this high frequency and high speeds. So we are all looking for coherent antiferromagnetic spin transport. So one way to realize coherent excitations, as we see from this conference a lot, is basically ultra-short pulses of light. I mean, we all know that they can drive coherent spin precessions in various types of antiferromagnets, and we know like even some term which is called antiferromagnetic optospintronics. But the problem is that when you try to drive, that's what David mentioned during his talk, when you try to drive spin waves using light wave, there's a huge mismatch between propagation velocity of light and the spin wave. So as a consequence, as you can see, you can drive only magnons which are very close to zone center, like to the center of brilliant zone. So basically, I mean, I'm not going to go discuss now about two magnon lines. It's a little bit different topic. So let me talk about like magnons which are still very close to zone center. So basically, if you're not talking about two magnon lines, then basically we can say that magnons which we are driving have k which is close to 0. And what you can see here, these magnons close to k, close to 0, they basically have the lowest frequency among all the magnons. That's one problem. But another problem that these magnons have a group velocity which is nearly equal to 0. So such magnons simply cannot be used to transport information. So how to solve this problem? One way to solve this problem actually is just to make some kind of inhomogeneous excitation. And like if you create a homogeneous excitation, so you localize your excitation, and then such excitation can serve a source in a reciprocal space. It can serve as a source of finite k vectors. And indeed, similar experiment have been performed, to be honest, on an antiferromagnet in an yttrium garnet, where people are focused tightly light, and then they see propagation of ferromagnetic magnons. I'm pretty sure that the same experiment can be done on an antiferromagnet. But the problem is that if you want to focus light, you, of course, will face some diffraction limit. So basically, it's very hard to go to excite spin waves with a wavelengths less than 1 micrometer. And of course, if you want to make ever faster magnons in both sense frequency and a spin wave group velocity, you want to go below. So is there any way to find a natural way to localize your excitation? And the answer is yes. What you can do, actually, you can use natural absorption. So almost every insulator has basically some sort of a bow band gap absorption. When absorption goes very much up, and as a consequence, penetration depth of light can be brought down to less than 100 nanometers. So essentially, that's a way to localize your excitation on a significant, on like way below the diffraction limit. So basically at least one order of magnitude less. And of course, if you create such a even stronger localized excitation, it serves as a source of all finite k vectors, which can be pretty large. I hope I will be able to convince you later on with some data. So our idea was, let's try to exploit the natural absorption to create wave packets of coherent magnons. So, all right, to realize it in practice, we considered a classical antiferromagnet, dysprosium orthoferrite. We heard from Rostislav today about this material, and this material is like has many advantages. Among them, it's actually a very strong light magnetism coupling. So all these citations, they show that you are able to derive coherent spin waves basically from visible to far infrared. So it's like we expect very good response to upon light excitation, but we wanted to study actually some sort of UV excitation. Okay, why UV? Because you can see here that if you look up optical absorption dysprosium orthoferrite, you can see the band gap absorption starts up about 2.5 electron. This is due to so-called charge transfer excitations, and this above band gap absorption results in a very short penetration depth. So you can see that for the photon energy of 3.1 electron volts, penetration depth falls down to 50 nanometers. So basically, it's at least one order of magnitude more than what you can get, less than what you can get by even diffraction limited focusing. So that was our idea. Let's just use this confinement due to absorption, and then basically to drive a wave packet of coherent magnons. So, and like when we were performing this experiment, we were simultaneously measuring two magneto-optical effects. First of all, a magneto-optical Faraday effect, for which we heard about this already many times during today and yesterday. So we measure rotation of the light polarization plane when the probe pulse is transmitted through a sample. But simultaneously with the Faraday effect, we track dynamics of so-called magneto-optical Kerr effect, or which is mostly known as a MOKE. So this effect basically quite oftenly used, and this is some special attention was paid to the MOKE effect. And the reason for this, the very first one, is quite simple, because we excite the spin waves close to the sample surface, and MOKE effect is surface sensitive. This reason is pretty obvious. So that was the idea basically to enhance sensitivity. But there's some other reason, which some other feature which we initially overlooked. And this feature is very much known to people which work in magnonics. Actually, when you work in a reflection geometry, and MOKE is experiment which is performed in reflection, you have a three waves process. That's an incident wave, reflected wave, and a spin wave. And all of these three waves have to be subjected to some conservation of momentum, which is written here. So you can see here that the k vector of wave which you detect depends on the k vector of the probe pulse which you are using to probe the dynamics. So basically, the MOKE experiment provides you possibility of the k-selective detection of the spin wave components of the wave packet. You can see it a bit different way that actually when spin wave propagates, it creates some sort of dynamical phase grating on which your probe pulse is basically being diffracted. All right, let me show you some results. So here you can see the dynamics which we measured. So we start with a Faraday effect. So we see quite clear oscillations. And based on frequency, we can identify this mode, and it corresponds to oscillations of spins around the y-crystallographic axis. It corresponds just to homogeneous spin precession. However, when we switch to the MOKE experiment, we also observed oscillations. But as you can see here, frequency of these oscillations is significantly higher. And when we plot them together, we can see that they are different by roughly 40 gigahertz. So they're clearly distinguishable, while the excitations are very same and probing is simultaneous. So one way to assume that maybe what we see is higher frequency oscillations is basically nothing more but a magnon at a finite k vector. And to confirm this, we basically actually we calculate the k vector based on a probe wavelengths, and we found out that this frequency perfectly falls down on dispersion relation which unites frequency and wave vector of magnons. Moreover, we try to play this angle of incidence and the wavelengths of our probe pulses. And what we can see is that actually we can be sensitive to a different spin wave components of the excited wave packet. And you can see here distribution of amplitude inside of this wave packet. And we are sitting somewhere here. And I would like to emphasize here that we were sensitive in our experiments to the spin waves with the wavelengths of around, like the shortest wavelengths which we can probe were around 140 nanometers. So significantly also shorter than what you see in the typical magneto-optical experiment with imaging. So just let me say a little bit about the characteristics of these waves and their use for, let's say, for the antiferromagnetic magnonics. So what we can see, we plot velocity as a function of wave vector, and here is waves which we were able to detect. And their group velocity is essentially 12 kilometers per second. 12 kilometers per second is actually quite high. It's 2 times faster than propagation of the sound. And the propagation of sound actually it is a limiting speed of the heat propagation. So we actually, these magnons propagate faster even than the heat propagates. Moreover, we estimated their lifetime of these excitations, and basically we estimated coherence lengths. And it's on the order of 1 micrometer. And I would like to here emphasize that this is like a lower bound for this propagation length. And this propagation happens at a frequency of 0.23 terahertz. So we also, this is basically some fresh results. So we tried to repeat this experiment on another orthoferrites family member, actually holmium orthoferrite. And surprise, we see the very same actually results. So we are also able to excite a finite K mode, and then also this mode at the zone center. But in holmium orthoferrite, we put a little bit more efforts, and actually we were able to map out a significant portion of the dispersion by varying the probe wavelength. So basically we were able to map out of 0.1 terahertz of the dispersion relations. And what's also remarkable that for the shortest wavelength magnons, we already reached this a linear regime of propagation when the propagation velocity reaches 20 kilometers per second, which is basically the limiting speed for the magnon excitations in this sort of antiferromagnets. I think because of sake of time, we see some also indications of some scattering events within this wave packet, but I would like to skip this just to be on time for the coffee. So I was asked at the very beginning to say some words about how these magnons actually can be used for the data recording. So what we have shown that you are able to interconvert ultra-short light pulse into some sort of spin wave pulse. They're still not ultra-short, it's just still dream, but such pulses, if we are able to interconvert them, they also carry a torque. And so as a consequence, in principle, they can be used to manipulate domain walls in such a way you can create some sort of antiferromagnetic racetrack memory and such a way to switch between antiferromagnetic beats. So this brings me to conclusions that I demonstrated you some all-optical excitation of a wave packet of coherent propagating antiferromagnetic spin waves. We verified this mechanism in a broad class of rare earth orthoferrites, and that's what I skipped, but this is some fingerprints of many body interactions within this wave packet, so which result to scattering. And I hope that within this work, I showed you that we create some sort of all-optical platform for future coherent antiferromagnetic magnonics. So just before the very end, I would like to thank all those people who contributed to this work, particularly to Jorit Hortensius, to the group of Andrea Caviglia, where this work has been performed, to the group of Rostislav Mikhailovsky, and particularly to Ruben Leinders, and also to our theoretician Boris Ivanov, Roberta Citra, and Alexei Kiviml. And thank you very much for your attention.